vector missions, which is also a kind of classification technique. So SVM is there for regression also, but we'll be discussing within in the context of the in the context of the classification problem. Okay, so we'll be discussing that what is the discriminant function, what is the linear discriminant function, and what is the classifier margin, and we'll then discuss the maximum margin classifier, which is nothing but the SVM. And then we'll be solving the optimization problem of the SVM. Then we'll be discussing the soft margin SVM as well as the kernel SVM. Then we will extend it to the multi-class classification problem. Okay, so this is the agenda. So we'll be discussing these topics in today's session. All right. So let us see what is this classification problem. We have already seen. Yesterday we had discussed one class. Day before we discussed one classification technique, which is logistic regression model, right? It is also similar to that. Okay, but the discriminant function, the intuition behind the discriminant function is different. So here also we have given the data set something like this. We have given x1, y1, x2, y2, so on xm, ym, where xi is the d-dimensional feature vector, yi is the corresponding discrete target value. The task is to predict for the new instances. So I hope all of you are familiar with the problem by now. What is the classification problem? You're familiar, right? What is the classification problem? So let us, yeah. So look at the discriminant function. So discriminant function is what? Discriminant function is a function that is trying to distinguish the instances of one class with the instances of the other classes, right? So it can be any arbitrary function of the input vector x, such as nearest neighbor, which is trying to distinguish or discriminate the instances of one class with the instances of the other class, as you see here. So it means anything that is falling within this boundary will be classified as a positive instances. Anything that is falling within this boundary, this side of the boundary, it will be classified as a negative class according to the k nearest neighbor. So it means the decision boundary is something like this in case of this nearest neighbor, right? One nearest neighbor. So if you take the decision tree, the decision boundary is something like this, which will be taking the sequence of decisions as you see here. This is one decision, this is another decision. It is taking the sequence of decisions on the attribute values and classifying the instances. So the decision boundary that it is forming is something like this, as you see in the second figure. So if you take the linear functions, then the decision boundary is decision boundary is like a line or a hyperplane that separates the instances of one class with the instances of the other class, right? The decision boundary is something like this: W transpose x plus b, where b is the intercept, W are the coefficient values. All right. So then if you take the nonlinear functions, some nonlinear decision boundary that separates the instances of one class with the instances of the other classes, right? If you observe all this, the decision boundary shape may be different, but the functionality of them is same. So what is that they are trying to do? They're trying to separate the instances of one class with the instances of the other class. They're trying to distinguish between the instances of the different classes, right? So that is what is the discriminant function is. They're trying to discriminate or distinguish the instances of one class with the instances of the other classes. That's what the discriminant function is, right? So in this lecture, we'll be mainly focusing on the linear functions. Then we will be seeing that how to extend it to the nonlinear setting. So we'll start with the linear function. Then we'll see how to extend it to the nonlinear setting. All right. So as I have mentioned to you that the linear function is kind of line or a hyperplane. So it is same as that, but here we have slightly used a different notation. W and B we have used instead of theta naught. So in our previous notation, B is equivalent to theta naught. This W is like a vector of all theta 1 to theta D. All right. So now it's the same, that it's a line equation or a hyperplane equation, line in the two-dimensional space and hyperplane in the multi-dimensional space. All right. So this is a we are trying to learn a line that separates line or a hyperplane, line in the two-dimensional space, hyperplane in the multi-dimensional space. So we are trying to learn a line such that it separates the instances of the positive class with the instances of the negative class. So we'll be dealing with the binary classification problem first. Then we will see how to extend it to the multi-class setting. All right. So this is a kind of a line W transpose X plus B equivalent to 0. We're learning this line such that all the positive instances will be above the line and all the negative instances will be below the line, right? So it means for all the positive instances, W transpose X plus B is greater than 0, and for all the negative instances, is W transpose X plus B less than 0. So we are learning this line W transpose X plus B is equivalent to 0, such that for all the positive instances, this W transpose X plus B greater than 0, and for all the negative instances, W transpose X plus B less than 0, right? So it means what? You're trying to learn a separating hyperplane such that all the positive instances lie above the line and all the negative instances lie below the line. That's what we're trying to do. Okay, and this is a line in the two-dimensional space, hyperplane in the multi-dimensional space. Here n is the unit length vector which is perpendicular to this line. Okay, so because W is perpendicular to this line, as W transpose X plus B is equivalent to 0, W is a vector which is orthogonal to this line. So if you want to get a unit length vector, divide W by mod of W, you will get a unit length vector which is in the same direction as W, right? So W is the unit length vector which is in the same direction as W. This we're gonna use later. Okay, just keep that in mind. Right? Are you with me so far? Following, right?
Yes.
Yes, sir.
So now the question is, how would you classify these points using a linear discriminant function in order to minimize the error rate? Okay, so can anybody answer this question? How would you classify these points using a linear discriminant function or a line in simple words in order to minimize the error rate? Okay, so if you look at this line, what is the error? If you look at this line, what is the error? What is the
Yes.
error? Zero?
Yes,
Zero
sir.
error, right?
Yes,
If
sir.
you look at this line, it
Zero.
is correctly classifying all the instances. Zero.
Yes.
Zero error.
Yes.
You look at this line, this
One error, sir. Oh, now
this zero error,
zero error, sir.
Zero.
right? So there are infinite number of possibilities. You see that this line, 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 this line. There are many possibilities. All of them are correctly classifying this data. But which is the best line? Out of all these infinite number of possibilities, all of them are accurately separating the data. Which is the best line among all these lines is the question. Right? That's what the question that we are trying to address. There are infinite number of answers. You see that this line accurately separates, this line accurately separates, this line, this line. There are infinite number of possibilities. But which is the best among all these lines? Okay. So let's say that these are these two groups of houses. Let's say there are two groups of houses. Let us say all the green color points are one group of houses and all these yellow, white color points are another group of houses. You're an engineer. I've asked you to lay a road in between these two group of houses. You're an engineer. I've asked you to lay a road in between these two groups of houses. So which direction would you choose to lay a road? I'll give you options. Okay. Option 1, this direction. Option 2, this direction. Option 3, this direction. Which direction would you choose
D3.
to lay a road between two group of houses?
D3.
D3. So most of you said D3. Why is it so? Why not D1 or D2?
Less difference between the path and the other houses.
So it means if you lay a road in this direction 1 or direction 2, you will get a narrow road. Am I right? Width of the road will be very less, right?
Yes, sir.
Whereas if you lay a road in this direction, you will get a more width road, wider road, right? Am I right? Is that the
Yes,
reason
sir.
for choosing D3? Right.
Yes, sir.
Now the another question coming in here is that why wider road? Why not narrow road? To accommodate the
They
future
may-
requirements, right?
In future, their requirement may be more.
Yeah. So to accommodate the future requirements, you need a wider road. Okay. So now let us try to map it with our concept of the classification. There are points from the two different classes. You have multiple options. Okay. There are multiple possibilities. This line, this line, this line, infinite number of lines. So which is the best line among all these lines? A line that maximizes the margin is the best line. Can I say that? Margin means
Yes, sir.
you can say that like a width of that line before hitting the data points, right? So the line that maximizes the margin is the best line because it will leave more space on both the sides. The line with the maximum margin will leave more space on both the sides. So obviously, if the instances are coming from the same distribution, the class 1 instances will be more close to this group and class -1 instances will be more close to this group. So if there is a more place on the either side, it will be able to accommodate more number of points on the other side. It means there is a possibility of misclassifying these points is very less, right? So that is the reason why we need a maximum margin classifier, because it is giving the more space, right? So that it can accommodate more number of points. And if the points are coming from the same distribution, there is a higher chance that it is close to the existing points from that class, right? So if it is somewhere here, let's say there is a point somewhere here. Okay. So intuitively, if you look at this point, to which class it should belong to? If you look at the point, let's say this is the point. If you look at that point, intuitively, to which class it should belong to?
Negative.
Class B,
It should
Negative.
belong to negative class,
negative
right?
class.
Right? So, but suppose if there is a classifier something like this, how is it classifying this?
Sir, class positive.
It is classifying it as a positive class, right? So though it is closer to this negative class, it is classifying it as a positive class. So you'll not get such problem with a maximum margin classifier, right? Because it has the most space to accommodate on both the sides. So it will be able to classify it as a negative only. So the misclassification error for the future instances would reduce if you select a classifier with a maximum margin. So have you understood what is maximum margin classifier and what is the intuition behind selecting the line with the maximum margin or classifier with the maximum margin? Are these 2 points clear?
Yes, sir.
Everybody?
Yes.
sir.
Yeah. Thank you. So there are many possibilities. Which is the best line? So you see that if you take this classifier, intuitively if you look at this, it should belong to negative class, but it is classifying it as a positive class, right? But there is no such problem with the maximum margin classifier. So how do we define a margin of the classifier? Margin is the boundary or width of the boundary could be increased before hitting the data points. That is indicated with the yellow color shade in the figure, right? So width of the line that could be increased before hitting this data points of the either class. Thus we are calling it as a boundary. Sorry, margin, right? So the optimal classifier is the one with the largest margin, right? So this is the simplest kind of SVM that we are learning, right? So linear SVM, we call it as linear SVM, we call it as. Okay. So before we proceed further, are you with me? Following so far?
Yes,
Clear?
sir.
Yes.
sir.
Yeah. Thank you. So now, earlier what we were saying, we are trying to learn a line W transpose X plus B equivalent to 0, such that anything above the plane is positive and anything below the plane is negative. It means you try to learn a line such that all the positive points come above the plane and all the negative points come below the plane. That's what we are saying. So this was the earlier condition. So for all the positive instances, this W transpose X plus B must be greater than 0. It means all the positive instances should lie above the plane. And similarly, for yi equal to -1, for all the negative instances, this W transpose Xi plus B less than 0, right? So this is what we were saying earlier. But with the concept of this maximum margin classifier, you are inducing two more lines into the picture, which is acting like a positive boundary and the negative boundary of this classifier, right? So you see that in the figure, there are three lines. One is the positive boundary of this classifier, and another one is the negative boundary of this classifier, right? So this is the positive boundary, this is the negative boundary, this is the actual classifier, right? So you are creating two more lines here such that all the positive points should lie on or above the positive boundary, and all the negative points should lie on or below the negative boundary. Okay, so it means if you say that this is the W transpose X plus B equivalent to +1, if you say this is the W transpose X plus B is equal to -1, so now we redefine the conditions, like we rescale them and say that for all the positive points should lie on or above the positive boundary, and all the negative points should lie on or below the negative boundary. So these are the new conditions that we are defining, right? So we are not saying it should be above this line or below this line. We are now saying that it should be on or above the positive boundary, or it should be on or below the negative boundary. So all the positive points should lie on or above the positive boundary, and all the negative points should lie on or below the negative boundary. Okay, is that clear so far?
Yes, sir.
Yes,
Fine.
sir.
Yeah. So now, yeah, thank you very much for the responses. So now, how do we measure the margin of this classifier, right? I mean, width of this road, right? Or the distance between the positive boundary and the negative boundary, right? The distance between the negative boundary and the positive boundary will give the width of this margin. Am I right? But tell me, when you are measuring the width of this or the distance between the planes, which line would you consider to measure the distance between the lines? Will you consider this line or will you consider this line?
So the distance between the blue line to black line
Yellow.
and the red line to the black line will
Yellow
not be
and
the
yellow.
same also.
Will be same.
L1.
L1 we consider. Yeah, it's
Yes,
the
sir.
same, madam. This is in the middle. But anyhow, these are for our understanding, madam. Actually, these lines are not exist. Okay, we'll be learning this line only. Such that this is maximized. Okay, so this is all for the formulation of the concept. We are visualizing this. Okay,
sir.
madam. Yeah. Yeah, we'll be considering L1, right? Which means the perpendicular distance between this point, this line, and this line. Am I right? Right.
Yes, sir.
So let us take some arbitrary point which is lying on this line, negative boundary. Let us call it as a x1. Okay. Let us call it as x1. And let us say some point which is lying on x positive boundary and it is perpendicular to this point, and let us call that as a x2. Okay, so it means x1 is a point that is lying on the negative boundary, x2 is a point that is lying on the positive boundary, and it is perpendicular to this point, right? So if any point that is lying on the negative boundary, what is the value of it? W transpose x1 plus b. What is the value of this? If it is the point lying on this boundary, negative boundary.
-1.
It is equivalent to -1, right? If there is any point that is lying on the positive boundary, what is the value of it?
1.
One.
Plus 1. That means W transpose x2 plus b is equivalent to +1. Right? Do you agree to these 2 points?
Yes, sir.
Fine. Okay. So 2 lines are parallel. The 2 lines are parallel. Thus they share the parameters W and B. Right? So we pick up any arbitrary point x1 that is lying on the negative boundary. Sorry. And closest point on this line to x1, closest point on the positive boundary to x1 is the point which is perpendicular to this, right? So the closest point always lie perpendicular, right? Or do you think it in any other direction? Will it be
Perpendicularly.
only in the perpendicular direction, right? The closest point always lie perpendicular. So now can I say that to get x2, how do you get x2 from x1? x2 equivalent to x1 plus which direction should I proceed? In the perpendicular direction, isn't it?
Yes, sir.
And W is the vector which is perpendicular to this classifier. That's what we discussed in the previous slides. If it is perpendicular to this, will it be perpendicular to red line also? Will it be perpendicular to this blue line also? As they are parallel to one another? Hello?
Yes, sir.
Yeah. So W is the vector which is perpendicular to the classifier. Therefore, it is perpendicular to the positive boundary and the negative boundary as well. That means which direction would you choose? We choose the direction of the W, right? So start from x1, proceed in the direction of W. But where to stop? Somewhere you stop. Let us call that as a lambda, right? So x2 equivalent to x1 plus lambda W. It means start from x1, move in the direction of W till some point you will get x2. Is this true?
Yes.
Sir.
Right. Start with x1, move in the direction of W till some point you will get x2. That's what this equation is saying. Right. So I hope that is you agree with me that x2 equivalent to x1 plus lambda W. All of you agree?
Yes,
Till
sir.
this point? Yeah.
Yes, sir.
All right. So x2 equivalent to x1 plus lambda W. So the closest point always lie perpendicular and W is perpendicular to both. So now this lambda W is the line segment connecting both x1 and x2, right? But this is not the distance. If you want to get the distance, take the lambda mod W, that's the distance between them. That is what we are interested to find. But we don't know what is lambda. Let us solve for lambda. We don't know what is lambda. Let us solve for lambda, right? So solving for the lambda. We know that W transpose x2 plus B equivalent to 1. Why is that W transpose x2 plus B equivalent to 1?
Because it belongs to positive one.
Because x2 is a point that is lying on the positive boundary, isn't it? Right. So x2 is a point that is lying on the positive boundary. That's why this is W transpose x2 plus B is equivalent to 1, right? So now we know that x2 equivalent to x1 plus lambda W. So can I substitute this in the equation, in this equation?
Yes, sir.
So substitute, you get W transpose x1 plus lambda W plus B equivalent to 1. Expand this. When you expand this, W transpose x1 plus B plus lambda times W transpose W is equivalent to 1. Can anyone tell me what is the value of this? W transpose x1
Minus
plus
1.
B. Minus 1, right? Because x1 is a point that is lying on the negative boundary. So can I substitute minus 1 in that place?
Sir.
So we can substitute minus 1, right? So it is minus 1 plus lambda times W transpose W is equivalent to 1. So can I solve for lambda now? Lambda
Yes,
is equivalent to 2 divided by W transpose W, which is nothing but 2 divided by mod W square, right? So this is what is the lambda. But what we are interested in? We are interested in finding out the distance, right? And what is the distance? Lambda mod W, isn't it? So what is lambda mod W? Lambda mod W is 2 by W. W square times mod W, which is 2 by mod W, which is nothing but 2 divided by square root of W transpose W. So this is what we want to maximize. Clear? Or should I repeat something?
sir. Clear.
Clear. Fine. This is what we want to maximize. Okay, let us simplify it further. So intuitively, we want to maximize the distance between the boundaries. That means the margin 2 by W. So maximizing, I'm not calling it as a mod W every time just for the sake of convenience, but you can refer to the slides and get that. So maximizing 2 by W is equivalent to minimizing W by 2. Agree?
Yes, sir.
As they're inversely proportional to one another. So maximizing this is equivalent to minimizing this, inverse of that, right? And which in turn equivalent to minimizing W square by 2. Agree for this also? Because minimizing f of x is equivalent to minimizing f of x square, right? So minimizing W by 2 is equivalent to minimizing W square by 2. Agree, right?
Yes, sir.
But why are we doing this? Is the question that's running in your
So
mind.
how this has become W squared, sir?
How this become?
W squared. How it became W squared?
No, that's what I'm saying. That minimizing W by 2 is equivalent to minimizing W square by 2. See, you want to minimize some function f of x. Isn't it equivalent to minimizing 2 times f of x? I'm not saying f of x is equivalent to 2 times f of x. I'm saying minimizing f of x is equivalent to minimizing 2 times f of x. Please observe the difference. I'm not saying f of x is equivalent to 2 times f of x. They are different, definitely. But minimizing this is equivalent to minimizing this. Hello, ma'am.
Because we have to minimize in the both the direction. That's why it is W squared by.
I mean, for whatever parameter f of x is minimized, for the same parameter 2 times f of x will be minimized because it's just a constant multiplied by that,
Okay. Okay.
right? Or in other words, they're proportional to one another. Am I right, madam?
Okay, sir.
Understood? Okay. So minimizing, similarly here also, minimizing W by 2 is equivalent to minimizing W square by 2. Convinced now, Geeta madam?
Yes, sir. Yes.
Yeah.
But that is two constants. The square here.
No, I mean, it's just as long as they're proportional to one another, it's okay. If they're inversely proportional, maximizing one thing is equivalent to minimizing the other thing. Like here, maximizing 2 by W is equivalent to minimizing W by 2. Got it, madam? And this is a mod W, not direct square. Mod W, not the direct W square. Okay. Got it, madam?
Okay, sir.
Mod W is a scalar only. Okay. And this is a positive quantity only always. So therefore, minimizing this W by 2 is equivalent to minimizing W square by 2. Now the question is this. I posed a question that why is that we have to do this? Why not we directly solve this? Any answer?
So as to, as you said, so as to avoid the misclassification error, let's have to reduce the.
No, that is also the same, right? We are be solving the same problem. Through this way or this way, we'll be solving the same problem. Selecting the W that minimizes this, which is equivalent to selecting W that maximizes this. You'll be solving the same problem only. Problem will not be different. I mean, technically at least, there is, I mean, intuitively at least, there is no difference between them. Right? This is to simplify the mathematics. That is all. There is no reason behind that. Okay. We'll be solving the same objective, but we'll be simplifying the mathematics further. For this reason, we will be transforming the problem from one form to the another form. That's all. Okay. So is that point clear?
Yes, sir.
Yes. So now let us try to formulate it as a quadratic programming formulation. So what is our objective now? Our objective is to minimize this W square by 2. This is not only the objective. There are some subjective constraints. What are the constraints? All the positive points should lie on or above the positive boundary, and all the negative points should lie on or below the negative boundary. Isn't it so? Subject to these constraints only, we have to maximize this, right? Sorry, minimize that, right? So minimizing this is equivalent to maximizing the margin, right? So you want to minimize W square by 2 so that for all the positive points, this W transpose X plus B must be greater than or equal to 1. For all the negative points, this W transpose Xi plus B must be less than or equal to -1. Okay, so this is what is our problem. We want to minimize W square by 2 such that all the positive points should lie on or above the positive boundary and all the negative points should lie on or below the negative boundary. Okay, so far are you with me or lost anywhere so that I can repeat it now itself?
Yes, sir. Yes, sir. Yeah, yes,
Geeta ma'am, your voice is badly breaking actually. You following?
yes, sir. Yes, sir. Yes, sir.
Did anybody understood what she said?
So she is saying we are with you. You can
Okay,
continue.
okay, thank you. Okay. Yeah, so now a question to you. Here there are two conditions, right? So can you find any common pattern between them so that we can represent them as a single condition instead of writing them as a two conditions? Do you find any common pattern between them so that we can represent them as a single condition? Anybody? So here it is saying whenever yi is positive, the corresponding W transpose xi plus b must be greater than or equal to 1. Okay, so can I also write it as the multiplication of this one and this one must be greater than or equal to 1? What is the resultant when you multiply plus 1 with greater than or equal to 1? What is the resultant?
So greater than 1 or
Greater
equals
than
to
or
1.
equal to 1, right? Okay, so see this case, what is the product of -1 times less than or equal to -1?
So positive 1.
This is also greater than or equal to 1. Am I right? When you multiply -1 with less than or equal to -1, what will you get?
Positive
You will
value.
get greater than or equal to 1, right? So can I write both the conditions using the simple condition like yi times W transpose xi plus b must be greater than or equal to 1 for all yi. This will take care of both the conditions, isn't it so?
Sir.
Right. So instead of writing two conditions, I can simply express this using a single condition that for all yi, this W transpose xi plus b must be greater than or equal to 1. Right. So this is what is the condition. Right. This is what is our objective function. We want to minimize this W square by 2 subject to the constraint that for all the instances, yi times W transpose xi plus b must be greater than or equal to 1. So this condition means for all the positive instances, W transpose xi plus b must be greater than or equal to 1. For all the negative instances, W transpose xi plus b must be less than or equal to 1, minus 1. It means all the positive points should lie on or above the positive boundary and all the negative points should lie on or below the negative boundary. That's what it means. Okay, so this is the problem at hand. So if you have any optimization problem that is of the following form, minimization of f of x subject to the constraint that g of x less than or equal to 0. If it is in this form, we can introduce a Lagrangian to represent the condition as part of the objective function. To represent the condition as part of the objective function, something like this. So f of x plus alpha times z of x subject to the maximization over alpha greater than or equal to 0, right? So now look at our objective function carefully and tell me, is it in this form? Minimization of f of x. We have also some f of x. This is f of x. Subject to the constraint that g of x less than or equal to 0. Is it in this form? Is it in the z of x less than or equal to 0 form? Do you have any z of x that is less than or equal to 0?
No, sir.
Not exactly in that form, but can you bring that into that form? Can you bring this condition into the form of z of x less than or equal to 0? Hello, not following?
Yes, sir.
Can we bring or not? Gita madam?
I'm just sorting out how it can be done.
Okay. Sneha madam, anybody else? Yash?
Yes, sir. We can bring it to that form.
We can bring it to that form. Okay. So let us try to bring it that form. So what are we saying here? Yi times W transpose Xi plus B greater than or equal to 1. Okay. So can I bring this one this side? If I bring this one this side, what will happen? Yi times W transpose Xi plus B minus 1 greater than or equal to 0. Okay. So if you want to make it less than or equal to 0, what should I do? Can I multiply it with minus 1? If this is greater than or equal to 0, minus of this will be less than or equal to 0. Alright? Right? So take minus 1. It means 1 minus yi times W transpose Xi plus B less than or equal to 0. Right? So yi times W transpose Xi plus B greater than or equal to 0. If you bring this one the other side, this is equivalent to this. When you multiply it with minus 1, 1 minus yi times W transpose Xi plus B less than or equal to 0. So now is it in that form?
Yes, sir.
Minimization of f of x subject to the constraint that g of x less than or equal to 0. It is exactly in that form, right? G of x is exactly in that form, right? So now let us introduce the Lagrangian to represent the condition as part of the objective function. But here, not just one Lagrangian. We need to introduce n Lagrangian, where n is the number of instances, because for each and every instance, this condition must satisfy, right? So, introducing n Lagrangians, right? Sum over I equal to 1 to n, maximization over alpha I greater than or equal to 0, alpha I times z of x. This is z of x. 1 minus yi times W transpose xi plus b is our g of x. Okay. So, have you followed how we got this?
Yes, sir.
ನೋಡು ಯಾವ್ಯಾವ ಪುಸ್ತಕ ಇತ್ತ ಎಷ್ಟು ಮಾರ್ಕ್ಸ್ ಅಂತ ನೋಡಿತ್ತ ಕಡೆಗೆ
Alright. So everybody understood this? How we arrived at this objective function?
Yes, sir.
Yes, sir.
Yeah. So this is our loss function. Loss function is what? This one. Minimize W square by 2, sum over I equal to 1 to n, maximization over alpha greater than or equal to 0, alpha I times 1 minus yi W transpose xi plus b. So if you take the minus common here, then it is minus of alpha I times yi times W transpose xi plus b minus 1 subject to the constraint that alpha I greater than or equal to 0. Okay. So, all right, we introduced the Lagrangian, we got this equation. But what is the intuition behind this objective function? Let us try to understand that. Intuition behind this objective function. Okay. What should be the intuition behind any cost function? We discussed it twice so far. What should be the intuition?
To minimize the error.
Minimize the error, but yeah, that is true. Minimize the error, but what error? What is the intuition or what is the penalty that you're supposed to add when the prediction is equivalent to the actual value? What should be the penalty that you should add when they are deviating? What is the penalty that we add if prediction is equivalent to the actual value? Whenever the prediction is equivalent to the actual value, what penalty you add to the cost function or the loss function? Am I audible? Am I audible?
Penalty, no, sir.
Sorry, madam?
We don't need to add any penalty, no, if both.
Zero penalty, right? If the prediction is equivalent to the actual value, we add a zero penalty to the cost function, isn't it? Because that is what we expect. We need not add any penalty. We need not penalize the loss. When the more the prediction is deviating from the actual value, the more penalty we add to the cost function, isn't it? That should be the intuition behind any cost function. We have seen it in the squared loss. We have seen it in the cross entropy loss in case of in the case of logistic regression model also, right? Agree? Do you remember now?
Yes, sir. Yes.
Yeah. So now let us see that whether that is happening here or not. Let me take a scenario. Yi is +1 and W transpose Xi plus B greater than or equal to 1. Is it a correct prediction or wrong prediction? Yi is
Correct
+1.
prediction, no?
Correct prediction
Correct.
only, right? Because we
Yes,
are
sir.
saying all the positive points should lie on or above the positive boundary, and this is on or above the positive boundary. Therefore, it should be a correct prediction, right? What is Yi times W transpose Xi plus B when Yi is +1 and W transpose Xi plus B greater than or equal to 1? What is the value of this? +1 multiplied with greater than or equal to 1. What is the value?
1.
Greater than or equal to
Greater
1.
Some
Am I
value
right?
which is greater than 1, sir.
Greater than or equal to 1. Yes. So what is the value of 1 minus greater than or equal to 1?
Some positive value. So,
Less than or equal to 0?
Negative.
Am
Negative
I right?
value.
When you
yes, sir.
subtract 1
Yes, sir. Yes.
minus some value
Yes.
which is greater than or equal to 1, the resultant is less than or equal to 0. Okay. So this is less than or equal to 0. What is the maximum value that you can get out of this expression when if this is less than or equal to 0? For which value of alpha I such that condition is greater than or equal to 0, alpha I greater than or equal to 0, for which value of alpha I times less than or equal to 0 will be maximum?
Equal to 1.
When it is 1 and it is less than or equal to 0, let's say this is some negative value. Less than or equal to 0 means it can be negative also, right? -2 also. And 1 is multiplied with -2. What will be the resultant? -2.
-2.
Is this the maximum value possible? No, right? Hello?
1 it is
0?
possible.
What about 0? What about 0? Alpha is 0. What will you get?
Right. So we have to take maximum. So if we are taking negative, then we should consider better 0.
Yeah, the alpha less than or equal to 0, it can be any value, right? Less than or equal to 0 means it can be any value which is less than or equal to 0. Only point I'm asking you is which alpha I is maximizes this alpha I times less than or equal to 0, subject to the constraint that alpha I greater than or equal to 0. Which alpha I maximizes this alpha I times less than or equal to 0? Obviously 0 only, right? If you choose any positive quantity, there is a chance of getting negative value. If you choose alpha equal to 0, maximum that you can get is only 0, which is the maximum value possible, subject to this constant alpha greater than or equal to 0. Am I right? Think about it.
Yes,
Do
sir.
you think, yeah, everybody think about it. Do you get any better value than 0 to maximize this for
No.
alpha I?
No.
No, right?
No.
So the maximum value that you can get out of this expression is 0. That is also for the alpha I value equivalent to 0. It means what? This is adding a 0 penalty to the cost function whenever the prediction is right. This is adding a 0 penalty to the cost function whenever the prediction is right. That's what is expected, right? So similarly, you take yi is equivalent to -1, W transpose Xi plus B is less than or equal to -1. Is the prediction right or wrong?
Yes.
Correct?
Yes.
So what is this yi times W transpose Xi plus B when yi is negative -1 and W transpose Xi plus B less than or equal to -1?
It will be positive value and
Positive.
more penalties.
Greater than or equal to 1? Okay. So what is 1 minus greater than or equal to 1? Less than or equal to 0? So what is the maximum value that you can get out of this expression? For which alpha you get that expression? It is again 0, right? So this is also the correct prediction. So therefore you are adding a 0 penalty to the cost function. Okay. So now let us take a different scenario. Let us take some wrong prediction. Yi is positive plus 1. W transpose Xi plus B less than or equal to minus 1. Is the prediction correct or wrong? Yi is plus 1. W transpose Xi plus B less than or equal to minus 1. Your prediction, your actual value saying it is a positive class. Your prediction saying that it is on or below the negative boundary. Is the prediction right or wrong?
No, sir, it will become 2.
No, I'm not talking about 2 or 3, whatever that value, we'll see that later. But look at this two things and tell me whether the prediction right or wrong.
Prediction is wrong, no, sir.
Prediction is wrong, right? Right, because your actual label is saying it should belong to the positive class, but your prediction is saying that it belongs to the negative class. So the prediction is wrong, right? So what is the multiplication of this? Yi times W transpose Xi plus B.
Positive 1.
Madam, plus 1 is multiplied with less than or equal to minus 1. What is the resultant?
Less than equal to minus 1.
Less than or equal to minus 1, right? So if
Yeah.
this is less than or equal to minus 1, what is 1 minus less than or equal to minus 1? Greater than or equal to 2?
True.
Yes,
Yes.
sir.
Greater than or equal to 2? So you want to maximize alpha I times greater than or equal to 2, subject to the constant that alpha I greater than or equal to 0. So for which alpha I this is maximized? For when alpha I is infinity, isn't it? So the above expression is maximal when alpha is equivalent to infinity. It means you are penalizing the misclassified instances. So whenever you have the correct prediction, you are adding a 0 penalty to the cost function through this expression. Whenever it is a wrong prediction, you are adding some positive penalty to the cost function. That's what the intuition behind this expression. Have you followed that point now? No? I see, I mean, minimum response today. I don't know the reason. Is it due to your workload or you couldn't follow the session? Following the session?
Yes, sir.
It is too typical, sir, right?
Yes, sir.
Yeah, I understand this is slightly difficult to follow because the subject is that, but you are here to learn the difficult things only, right? Or you want to learn only the easy things?
No, sir, till now you have made so many difficult things easy.
Easy? Oh, this is not, I didn't make it easy. Alright, I mean, don't worry about it, madam. But if you couldn't follow something, please let me know. I will try to explain in different ways. Geeta, madam.
Sir, it is like we will sit and then again write, then we will be able to understand. But 95% we understood.
Okay, alright. Fine. So this is what the intuition behind that expression, right? So W transpose, I mean, whenever the prediction is equivalent to the actual value, this expression is giving the value of 0. It means you're adding a 0 penalty to the cost function. Whenever the prediction is deviating from the actual value, this expression is adding some positive quantity to the loss function. And the objective is to minimize the overall loss. All right. Fine. So this is what the expression that we have discussed, and this is the primary problem. Okay. So the loss function is this. Loss function is this. All right. So now, if you look at this, there is a minimization and there is a maximization. And this function is a minimization of maximization. Okay, you want to minimize it over W and B, maximize it over alpha I. There are two things in this. Multiple objectives, minimization of maximization. When you have any expression something like this, you can define the dual problem for this by interchanging max and min. Okay, we can define the dual problem of the primary problem by interchanging max and min. So if I interchange max and min, what will I get? Maximization over alpha I and minimization over W and B. Am I right? Hello, everybody.
Yes.
Right.
Yes, sir.
So you are interchanging max and min, maximization over alpha greater than or equal to 0, minimization over W and B, and solving the same problem. W square by 2 plus sum over I equal to 1 to n alpha I times 1 minus yi W transpose xi plus b. So there is very, what is that? If you really understand this idea, no, you will appreciate it very, very much, right? So it's a really, you will feel, very satisfied with this ideas, right? So now to see the beauty of it, you are creating a dual problem and solving the inside problem. After solving the inside problem, you are making it completely independent of W and B, and then solving the outside problem. Let's see how that how is that happening, right? So now it is the maximization of minimization problem, and now let us solve this problem. Whatever is inside, let us solve that problem. So this is the primary problem, inside problem, that we are trying to solve, right? It means we want to minimize this subject to W and B. It means you want to learn W and B that minimizes this cost function, which is what is the inside problem, this problem, right? So you want to learn W and B, you want to learn W and B such that this is minimized. Okay, so if you want to minimize anything, right, let us say your cost function Z or the loss function LP versus this W. Let's say it looks something like this. What is the slope of the function at the optimal point? What is the slope of the
Zero.
function? Zero slope, right? Zero slope. Everybody agreed for this? What is the slope
Yes,
of the
sir.
function at the optimal point?
0.
0, right? So if I want to get the optimal point, can I get the slope and equate that to 0? Will I get the optimal point?
Yes, sir.
How do you get the slope with respect to W? Take the partial derivative of the loss function with respect to W. I will get the slope, right? And equate that to 0. Okay. So take the partial derivative of the loss function with respect to W and equate that to 0. And solve that expression. When you solve that expression, you will get W equivalent to sum over I equal to 1 to n alpha I yi xi. So I want you to try this take this as a homework and solve this. Take
Your voice is not audible.
So there are some audibility issues, sir. They are unable to hear you, sir.
Am I audible?
Yes, sir. Now you are
Now
audible.
you are audible, sir.
Now audible. In between, I think I disconnected, isn't it?
Yes,
Because
sir.
my
Now it is audible,
yeah,
sir.
now it is audible. So yeah, I was saying that you must try this at home. Take the derivative of the loss function with respect to W and equate that to 0 and see that whether you're getting this expression or not when you solve it. Okay. But now, for now, you just follow what I'm saying. Right. When you take the derivative of the loss function with respect to W, equate that to 0, you will get W equivalent to sum over I equal to 1 to n alpha I yi xi. Okay. So similarly, if you want to get the optimal point with respect to B, what should I do? Take the derivative of the loss function with respect to B and equate that to 0. So you will get the optimal point with respect to 0. So tell me, just for the confirmation, that why is that we are equating it to 0? This one or this one? Why is that we are equating it to 0?
To getting the slope, sir.
To reach to optimal point.
We are interested in knowing what is the optimal point. And we know that at the optimal point, the slope is 0. That's why we are taking the slope and equating that to 0 and solving that to get the optimal point. Is that clear? That point is clear, right?
Yes.
Right. So you take the derivative of the loss function with respect to W and B and equate them to 0. You will get these two expressions as a result. Okay. Now substitute W equivalent to this expression in this equation and make use of this expression. Sum over I equal to 1 by n alpha ya. Right. So when you substitute this W in this equation, somewhere you will get this expression. So instead of that expression, you use 0. Right. Then you will get the resultant as this expression. This is actually looks tough, but it is very simple. I will explain it one more time. Please follow it. Okay. So till the dual problem you have understood, right? How did we get the dual problem? By interchanging max and min, right? So now we are trying to solve the inside problem, which is the minimization problem, which is this. We want to minimize this, right? So now to get the minimum point of or the optimal point of the minimization problem, we are taking the derivative of that loss function with respect to W and with respect to B and equating them to 0. When you equating them to 0, you got these two expressions, W equivalent to this and sum over alpha ya is equivalent to 0. Right. So till this point, is it clear?
Yes, sir.
Yes, sir.
Yeah. So now substitute W equivalent to this in this expression and make use of this expression. You will get the resultant as this expression. That's what I am telling. Clear, right?
Yes, sir.
Right. You can even try that. So after substituting W equivalent to this in the objective function and making use of this expression, we get the dual problem as this. Please observe this carefully and tell me, do you find any W or B in the expression? In the objective function? Look at this carefully and tell me, do you find any W or B in the expression?
Yes, sir.
Do you find any W or B in the expression?
Yes, sir.
Now it is not there.
The summation of AI, YI, and XI.
No W, no BI, right?
Yeah.
No B, right?
Now
W is not there, B is not there in this expression, isn't it?
Yes,
It
sir.
it
means
is
what,
P of W and B.
madam? Your voice is actually very low for me, Geeta madam, today. I don't know why. But others can hear her properly.
No, sir.
The equation is free with W and B, sir.
I couldn't follow actually.
She is saying something that can you prove that
No. I'm saying the equation is free with W and B parameters.
Did anybody understood?
no, sir.
Any understanding?
Have-
Ma'am, can you please type in the chat box because none of us can clearly hear you. Geeta madam, please type it in the chat box. Fine. So yeah. So here, if you see this, it means we have completely solved the inside problem. We solved this problem and made this whole problem completely independent of W and B. It means you're just expressing it in terms of alpha I, right? Just expressing it in terms of alpha I. You see that? Do you find any W or B? Yes, Geeta ma'am. Yeah, you're right. The objective function is now free from W and B. Yes, that's what she was saying. Yeah, please check your microphone, madam. We are actually missing you. You give prompt responses and we are not understanding. or else you can use your computer audio. Remove the headphone or something. Fine. Yes. So made it completely independent of W and B. Okay. So I'll confuse you now. I'm saying I'll confuse you now. Okay. Ready for the confusion. What is our problem? What we started with? Classification problem. And we started saying that we want to learn a line that separates the instances of one class with the instances of the another class. Then we said that not any line, we want to learn a line that maximizes the margin. Hello, isn't it that we said?
Yes, sir.
Right. And what characterizes the line? W and B, isn't it? W and B are the parameters of the line, and we want to learn a line that maximizes the margin. Right. It means we want to learn optimal W and B. Optimality is decided by a line with the maximum margin. Right. And then we started formulating the problem. Maximizing the margin is equivalent to minimizing W square by 2, subject to the constraint that all the positive points should lie on or above the positive boundary and all the negative points should lie on or below the negative boundary. Right. Then we did something, finally we got this. And here now we are saying that the objective is completely independent of W and B. You are interested in learning the optimal parameters W and B. Now you made it completely independent of W and B. What is that you are trying to achieve there? You are interested in learning W and B only, right?
Yes, sir.
Then why is that you made it completely independent of W and B? You started saying that you want to learn a maximum margin line. It means the optimal parameters W and B that maximizes the margin. And now you made the problem, or you derived the problem which is completely independent of the W and B. What is that we are trying to achieve here? Okay. So don't get confused with that. Later also you may get this doubt. That's why I've confused you before itself to clarify this. Okay. Here we made it completely independent of W and B to solve the problem, but we are not completely avoiding W and B. You made it independent of W and B so that you can learn the optimal alpha I. Once you made it independent of W and B, now can you solve this maximization problem or not? Because you just want to learn an optimal alpha I that maximizes this. Hello, can you learn the optimal alpha I?
Yes, sir.
Nobody is following. Can you learn the optimal alpha I or not? Not following, not following. Till this point, is it clear? How did we arrive at this maximization problem?
Yes, sir.
So, you say yes or no. I don't mind.
Yes, sir.
Yes, sir. Up to
Even if you say no, I don't mind. I will repeat. I'll ensure that you will understand the problem. Don't worry about it. Don't hesitate to say no or ask me to repeat something. So I'm asking again, have you followed this point? How did we arrive at this problem, maximization problem?
Yes, sir. Yes, sir.
Yes. Okay. Now the question to you is, the question that I was asking is, why is that you made it completely independent of W and B while you are looking for optimal W and B? That's what the question that I have asked you. Isn't it? Did you get that question? What I asked?
Yes, sir. Yes.
Yes. Now I am answering that question. Right. The answer that I am giving you is that once you made it independent of W and B, you can learn the optimal alpha I. Isn't it so? Now this is the function of only alpha I. You want to learn the optimal alpha I. I want to learn alpha I that maximizes this. Can I learn this or not? Using gradient descent algorithm or whatever. I can learn it, right? I can learn the optimal alpha, right? Because it is simplified version of this, right? It is made up completely independent of other parameters. It is just a function of alpha I. So now it is just a function of alpha I. I just have to learn the alpha I that maximizes this. Now your Objective function is something like this. This is alpha I and this is the loss function. And this is the objective function. Let's say J, right? You want to learn an alpha I that maximizes J, this point. Can I learn it or not? That's what I'm saying. You don't know how to learn. Is it our problem?
Yes, sir.
Sir, yes, sir.
How to learn? Do we have any instances to learn this alpha, sir?
Madam, your problem with the maximization term?
Only the maximization part we don't.
Okay. Okay, that's what I'm not understanding. What is your problem? Okay, let me put it this way. If this is a minimization problem, it looks something like this. And let's say this is the parameter, some alpha or theta, whatever. And you randomly initialize if it is somewhere here. You are estimating the slope. If the slope is negative, you are incrementing it to reach to the optimal point. If the slope is positive, you are decrementing it to reach to the optimal point. Isn't it? In the minimization problem. Right. So now tell me, hello, is that right? Minimization problem.
Yes, sir.
Yes. Now let's say when you randomly initialize your alpha is somewhere here. Right. You want to reach to this point, optimal point. Okay. What is the slope here? Positive or negative? Slope is positive only, right?
Yes, sir.
Yes, sir.
Positive.
Yeah, why are you thinking so much? Yes, positive only. What should I do? Increment or decrement to reach to the optimal point?
For increment,
Increment. If the slope is negative, then
decrement,
decrement. It's called gradient descent algorithm. Opposite of gradient descent. What are you doing in gradient descent? If the slope is positive, you are decrementing. If the slope is negative, you are incrementing. What you are supposed to do in gradient descent algorithm?
for opposite of
Sir,
that.
is it the complete reverse of whatever we used to do with the gradient descent? No,
Madam.
is it the reverse of the gradient descent thing now which
It
we have
means if
learned?
the slope is positive, you have to increment. If the slope is negative, you have to decrement. Yes. This is a minimization function. This is a maximization function. Okay. I just want to tell you that there are some optimization algorithms using which you can learn the optimal alpha. That's what I am trying to convey you. Is that point clear? How it solves? Let us not bother about this at this point. You just think about this, that you made the problem independent of W and D. Now you are solving for alpha I. Using some algorithms, you got this, let's say alpha I. You can use this optimal alpha I to obtain optimal W and optimal B. That is as simple as that. Don't think much. Okay. So let me summarize the steps that we have discussed so far. So what are the steps that we have discussed so far? The first thing is that we are trying to learn a classifier that maximizes the margin. It means you are trying to learn the optimal W and B. Okay. So maximizing the margin is equivalent to what? Minimizing W square by 2, subject to the constraint that all the positive points should lie on or above the positive boundary and all the negative points should lie on or below the negative boundary. To represent the condition as part of the objective function, we use a Lagrangian. We introduce a Lagrangian to represent the condition as part of the objective function. I introduce a Lagrangian. Now we got what? Minimization of maximization problem. How did we define the dual problem? Dual problem. Maximization of minimization. Now you solve this minimization problem, make this problem independent of W and T. Now you got a maximization problem which is independent of W and D, only dependent on alpha I. Now learn optimal alpha I by solving this maximization problem. Now the next step is use this alpha to get optimal W and B. That's what, as simple as that. Very elegant algorithm.
Yes, yes, sir.
Okay, is the steps clear now?
Yes, sir. You said no, with this one problem, we'll solve another problem.
Yes, yes.
So using alpha, by learning alpha, we are able to get optimal W value and B value.
Optimal W and B value, it means you are getting the maximum margin classifier. Because optimal W and B corresponding to a maximum margin classifier. Clear, everybody? Ash, Ravi sir, Sneha madam, everybody, sir?
So can you explain the steps again?
Yeah, sure. I'm just, let me find a space that where can I write? Okay, let me write it here. Step 1. Maximize the margin. Learn the maximum margin classifier. And we proved that maximizing the margin is equivalent to what? Minimizing W square by 2 subject to some constraint. Okay. Clear? So far,
Yes,
is this
sir.
clear? Yeah. Now, we introduce a Lagrangian to represent the condition as part of the objective function. Clear? Third step also clear?
Yes, sir.
When you represent the condition as part of the objective function, you have got this minimization of maximization. Minimize it over W and B, maximize it over alpha. Clear?
Yes, sir.
Right. Fourth step. Define the dual problem. How do we define the dual problem? By interchanging min and max. So now you said it is not minimization over W and B, maximization over alpha. Interchange this max and min. Now it is a maximization over alpha and minimization over W and B. Okay. So to solve this minimization problem, you took the derivative of this minimization problem with respect to W and equated that to 0. Took the derivative of this loss function with respect to B and equated that to 0. You've got some expressions out of it. Making use of these expressions, you made this minimization problem completely independent of W and B. Now it is just a function of alpha I values, right? So now you solve this inside problem and made it independent of W and B. Now you got a function maximization over something which is independent of W and B. Using this, you can obtain optimal alpha. Obtain optimal alpha. After obtaining optimal alpha, next step is obtain optimal W and optimal B by making use of optimal alpha. By making use of optimal alpha. So see the elegancy of this. See the beauty of this. Okay, you will really appreciate it if you understand this problem. Understand this solution.
Yes, sir.
Now you started saying that I want to learn a line that maximizes the margin. Line means there are parameters W and B. It means you want to obtain optimal W and B. But that's not so easy, right? Because there are some constraints. Constraints are what? All the positive points should lie on or above the positive boundary, and all the negative points should lie on or below the negative boundary. So both the conditions you represented as a single condition, and you have introduced a Lagrangian to represent the condition as part of the objective function. Then it became this minimization over maximization. Now you define the dual problem, maximization over minimization, and solve the inside problem first. Right? and made this problem independent of W and B to simplify it so that you can learn the optimal alpha easily, right? Using some off-the-shelf quadratic programming solvers or some projected gradient descent algorithms, you obtain the optimal alpha. Once you obtain the optimal alpha, make use of that and obtain optimal W and B. So now you got this W and B corresponding to the maximum margin classifier. Got it right? The whole processor?
Yes, sir.
Right. Everybody, any queries so far? Are you with me?
Yes, sir.
Yes, sir. Yes, sir.
Yes,
Sir.
Yeah. Geeta madam, is it clear now?
It was clear earlier only, sir.
Okay, fine. That's good. So now, yeah, that is completed. That we called it as a hard margin SVM. Okay, hard margin SVM. Whatever that we have discussed so far is a hard margin SVM. I'll tell you why is it hard margin later. Okay, but before that, tell me this. Look at this data carefully. All the green points are the positive instances and all the white circles are the negative points. Tell me, is it possible to draw a line that separates the green circles with the white circles?
No, sir.
Not possible, right?
No,
At least two of the points will be misclassified for any line, right?
Yes, sir.
It means this data is not linearly separable. Correct?
Yes, sir.
It's not possible to draw a line that separates the green circles with the white circles. So therefore, this is not linearly separable case. This is not linearly separable case, non-linear case, right? But tell me, is it due to very few points or by nature itself this is non-linear?
only due to less points.
Only 2 points, right? Because of these 2 points only, this is not linearly separable. If you exclude these 2 points, this is linearly separable only. Am I right?
Yes, sir.
It means there may be some noisy points or the outlier points that is inducing non-linearity into the data, right? So if you exclude those points, it is linearly separable only, right? So this may be due to some noisy or the difficult data points or the outlier points, in a sense that, like for example, while labeling the data, instead of labeling it as a green or a positive, somebody might have labeled it as a white or negative. Instead of labeling it as a positive, somebody by mistake as a typo might have labeled it as -1. Similarly, while labeling this, instead of labeling it as a -1, somebody might have by mistake labeled it as a +1. That possibility is there, right? Right. So there may be noisy points or the typos in the data. Because of that, they are by mistake labeled it as a positive or negative. That induces difficulty into the data set or non-linearity into the data set. So how to deal with this kind of cases? Okay. So if you take the hard margin SVM, that whatever that we have solved so far, right? If you take the hard margin SVM, what it is saying, all the positive points should lie on or above the positive boundary and all the negative points should lie on or below the negative boundary. Isn't it so?
Yes, sir.
Or is it possible to get such line so that all the positive points should lie on or above the positive boundary and all the negative points should lie on or below the negative boundary? Is it possible? It's not possible. If you try hard to incorporate these noisy points into the model, it will overfit to the data. It means the performance of the overall model will be degraded if you try hard to incorporate these noisy points into the model, right? Because these are just the hard points. Okay, so it means what I am trying to tell is that our model should have some flexibility to ignore the hard points or the noisy points, right? Suppose if I ignore these 2 points, okay, it's okay to misclassify them, I don't mind. but our model should be correct with respect to all the other data points. Suppose if my model has that flexibility, then it is easy to fit this kind of model so that every other point is correctly classified, ignoring those two. Hello, am I right?
Yes, sir.
Right. It means your model should have that flexibility to ignore them, flexibility to misclassify. You may think that why the flexibility to misclassify? We have the flexibility to misclassify hard or the noisy point, not every point. Okay. So because if you try hard to incorporate them, then it will degrade the overall performance of the model. That's the reason why it's okay to misclassify rather than degrading the overall performance. Right? It is okay to misclassify some of the points rather than degrading the overall performance of the model. Isn't it so? Hello, agree to me?
Sir, but there can be more points like these.
Then that is a different case. That also we'll see in the later slides.
Okay.
Okay. So this is only the case that I'm talking about is when there is such models, such points, noisy points, few points, or the difficult points, few points, hard points. Okay.
Okay, sir.
Fine. So how to induce that flexibility into the model now is the question. That's what the soft margin SVM is doing. Soft margin SVM. Okay. So soft margin SVM provides some flexibility in terms of the condition. So what the hard margin SVM says, what is the hard condition that we have? Hard condition that we have is that all the positive points should lie on or above the positive boundary and all the negative points should be on or below the negative boundary, right? Now you are relaxing the constraint. You see that earlier your condition is for all the positive points, W transpose Xi plus B must be greater than or equal to 1. Now you're relaxing that, right? So it should be greater than or equal to 1 minus the slack variable. Not saying 1 minus the slack variable. See the relaxation, right? It's okay to misclassify it with some slack variable margin, right? So you see that the slack variable here, right? It means you're providing the flexibility to misclassify this point. It's okay to have it in the distance of slack variable. Should be greater than or equal to slack variable. Similarly, earlier you're saying all the negative points, this W transpose Xi plus B must be less than or equal to -1. And now you're saying you're giving a relaxation. It should be less than or equal to -1 plus slack variable. So you're giving some relaxation for some slack variable greater than or equal to 0. You don't know what that it is. Okay. Alright. Is it clear so far? Are you getting any
Sir.
doubt? Any doubt?
Are we misclassifying or we are removing that point?
We are misclassifying that point. We're giving some flexibility. I mean, it's okay to have it greater than or equal to, let's say 2, it is 2. I mean, it's okay to have it greater than or equal to 1 minus 2. It means greater than or equal to -1. It means you're misclassifying that only, right? Hello?
Okay, sir. Okay, sir.
Yeah. Right. So now, tell me one thing. Is it okay to misclassify a few points or is it okay to misclassify all the points? What I'm trying to ask you is that should we give the flexibility to misclassify to the hard points only, or should we give the flexibility to misclassify to all the points?
Only to the hard points.
Only to the hard points we should give the flexibility, right? Okay, it means the flexibility that you are giving, right? So other points shouldn't take the advantage of that flexibility, right? Only the hard points can take the advantage of the flexibility, but at the same time, if there is some easy point that can be separable through the linear line, that point shouldn't take the advantage of this flexibility, right? So what I'm trying to tell you is that for most of the data points, the slack variable must be 0. For very few points where this separation is not possible, right, or they are the hard points, they can make use of this slack variable and misclassify it, right, using the slack variable greater than 0. But otherwise, for all of them, it should be equal to 0, right? So it means what? This is giving the flexibility. At the same time, it should have some mechanism to control the misclassification of all the data points. Otherwise, it is a serious problem that everybody will be misclassified with a margin of slack variable. Right? So it means in addition to maximizing the margin, now you have got an additional objective of minimizing the summation over the slack variables. It means for most of the data points, it should be 0. It means what? It is still the hard margin for most of the SVMs, sorry, most of the points. But at the same time, it is giving some flexibility to misclassify some of the hard or noisy points. Right? That's what it means. Fine. So that flexibility is given to this slack variable through the slack variable, right? So you are giving that flexibility. At the same time, you are minimizing summation over all the slack variables. It means you want it to be as minimum as possible. It means for most of the data points, you want it to be 0. When the slack variable is 0, what are the conditions? W transpose xi plus b greater than or equal to 1, and W transpose xi plus b less than or equal to -1. Isn't it so? When the slack variable is equivalent to 0. Hello?
Yes, sir.
Yes, sir.
I actually feel very worried if you are silent. Okay. Following, right?
Yes, sir.
Yes, sir.
No? Not following? Please let me know. I don't mind. Really, I don't mind. I'll just try to explain it in different words. Are you following or not?
But finding the hard point is difficult also.
No, you need not worry about that. You see, you don't have that. I mean, you don't have any way to find out what is the hard point, what is the soft point. The model will take care of it. How is the model taking care of it? It is just trying to minimize the summation over all the slack variables. Okay, it means automatically it will minimize the summation over the slacking variable. Means what? Automatically for most of the points you're making it 0. Okay, if there is any hard point that is not possible to minimize the slack variables, that's okay, it will leave, because you're just trying to minimize, you're not trying to make it 0. Right? So the model will automatically take care. It's not like that you'll be identifying what is hard point, what is soft point. You're not identifying that and setting the corresponding alpha value. Then there is no beauty of the machine learning, right? So machine learning is automatically doing all this. You're just formulating an objective function. The objective minimization of this objective function will take care of everything. I'm just trying to explain the intuition behind that formulation. That's all. Clear, madam?
Okay, sir.
Yeah. So here, everybody, please let me know. Do I have to repeat this slide? I felt that I shouldn't have skipped yesterday's class.
No, sir. I understood.
Okay, fine. Fine. Ash, what about Ash, Geeta madam, Ravi sir, many other who were responding? Clear to you? Or should I repeat some?
Yes, sir.
Yes, sir. Yes, sir. We could able
Yes,
to
sir.
understand.
Okay, all right. Fine. So yeah. So this is what is the current objective is. We want to minimize W square by 2 and summation over these slack variables. And this is C is like a weightage that you give to this part of the objective function. It's like a lambda in case of regularization term. Okay. Fine. So now a different case. What if the data is not linearly separable by nature itself? Like you see that this is the data. Is it linearly separable, this data set? Is it possible to draw a line that separates the blue points with the red points?
No, sir.
No.
Right. If you draw this line, all this will be misclassified. If you draw this line, all this will be misclassified. Right. But to solve these kind of problems, we have a non-linear SVMs. They will transform the problem to some higher dimensional space and learn SVM in the higher dimensional space. So like for example here. So this is the one-dimensional data and that is not linearly separable. Now you're adding another dimension, x square. Now you represent the data points with 2 dimensions, x as well as x square. Now you see that in the two-dimensional space, there is a linear separation. So non-linear in one dimension, linear in the two dimension, right? So this is another example. In the two dimension, it is not linearly separable. The moment you transform the problem to some higher dimensional space, there is a hyperplane that separates the blue points with the red points. Other examples also, you see that this is an example of X only one dimensional data. This is the two dimensional data after mapping X and X square. There is a separation between the positive and the negative points. So the model is linear in the new representation, but it is non-linear in the old representation. It means when you express the model in terms of the original data features, then this is non-linear in nature, right? So the linear in new representation is equivalent to non-linear in the old representation. Similarly, this problem. In the original space, it is x1 comma x2. In the transformed space, you have three features. Those are x1 square, square root of x1, x2, and x2 square. So what kind of features that you generate in the transformed space is depending on the kernel function that you apply. Kernel function that you apply. All right. That's the only difference, right? So if you apply different kernels, you will get then different sets of features, right? So now extending it to the kernel function is the same, right? Because instead of taking xi, now you are taking the transformed xi, which is the function of xi, psi of xi, right? Earlier you're just taking xi. In place of that, you just take the transformed xi. Similarly, the dual problem is also the same. Instead of taking xi transpose xj, you're taking the transformed xi transpose transformed xj, right? It means x are the feature vectors in the new representation you are taking instead of taking the old feature values, right? That's the only difference. Otherwise, it's the same. All right. So is it clear so far? Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So far, to summarize, we have discussed classification using the support vector missions. Okay. So then here in this problem, we started discussing the discriminative function. Discriminating function is any function that separates the instances of one class with the instances of the other classes, right? So we discussed different discriminating functions like nearest neighbors, decision trees, linear functions, non-linear functions. Then we started discussing linear functions. Linear function is a line that separates the instances of one class with the instances of the other class. Then we said that not any line, maximum margin line, line with the maximum margin is the best line because of some intuitive reasons, right? And later we derived that maximizing the margin is equivalent to minimizing W square by 2 subject to some constraint. Then we represented these constraints as part of the objective function and defined the dual problem, minimization over maximization. Then, we defined some primary problem using the Lagrangian. Then we defined the dual problem by interchanging min and max. Then we solved the inside problem, which is the minimization problem, made it completely independent of W and B, and then solved this maximization problem and obtained alpha I. Optimal alpha is. Once you obtain the optimal alpha I, making use of them, we obtain optimal W and B. So that is the hard margin SVM. Problem with this is that even if there is a single point which is a noisy point, that will try hard to incorporate that into the model, and it will lead to the performance degrade of the overall model. To avoid that, we provided some flexibility in the model through the slack variable, and we call that as a soft margin SVM, in which we are giving the flexibility. At the same time, we are controlling this flexibility by adding the summation over the slack variables to the minimization objective, right? So this we called it as a soft margin SVM. What if the data is not linearly separable by nature itself? Then we transform the problem to some higher dimensional space by applying a kernel function, and then we can use a linear SVM to solve the problem in the higher dimensional space, right? So it means you're transforming the nonlinear problem to a linear problem by transforming the data itself and then applying the linear SVM in the higher dimensional space. So this linear SVM in the higher dimensional space is equivalent to non-linear SVM in the original dimension, right? In the original space, right? That's what we have discussed so far. So all these concepts, whatever that I have summarized so far, all these are clear to you? Any query? Clear? Everybody, please. Any
Yes.
query? Clear. Okay. So shall we discuss multi-class SVM today only, or shall we continue it tomorrow? It takes around 35 minutes to 40 minutes. Or today or tomorrow?
Tomorrow.
Tomorrow.
will do.
Okay, fine. All right then. Thank you very much.
Once we'll see the sun comes.
Madam, Ramya madam.
Once we'll recollect the sun comes, then we'll be able to.
Yeah. I will. PPTs are already shared. So go through the PPTs if you have any query. And I want you to do this. That there are few things I've directly mentioned in the slide, like the derivative of the loss function with respect to W and equate that to 0, you will get this. Like that I've directly mentioned in the slide. I want you to solve that by hand. Take the derivative of the loss function with respect to W, equate that to 0, and see that whether you're getting that expression or not. Similarly with respect to B. And one more thing, I said that substitute W expression in the function and make use of this B expression, then you will get so and so equation, right? I didn't derive it completely to avoid confusing you, but I want you to derive it on your own, right? Then you will understand it very clearly. Then we will see the multi-class SVM. Okay, I want you to please do these two things, the derivation part as well as the substitution part. Okay, yes. All right then. Thank you very much and happy learning. Code also will demonstrate tomorrow.
Thank you, sir.
Thank you.